So here we are, still looking at discrete random variables, probability distributions associated to a random variable. What we want to look at today is how we can modify a random variable and use that modification to help us quickly process and find the expectation and the variance. So, if x is the original random variable, how could we quickly find modifications of that x value? In this instance, let's say that x is the number of vehicles that a student needs to get to travel to school. So, are they using 0 vehicles, potentially walking to school? Are they using just the 1 vehicle? Maybe they get driven to school by a parent. Or are they using 2 vehicles? A train for the main part of the journey, and then a bus up to the school gate. We've already seen how to find and calculate the expectation. In this case, the expectation is 2.4. If we modify this discrete random variable and we decide that now actually we want to focus on how many vehicles they get per day, so this is the journey into school and the journey home, well, that's going to be a distribution like this. The probabilities associated all stay the same, but the top row has doubled. If you're tracking the story or the context, this is because if they get 1 bus into school, they get 1 bus home. If they have to take 2 vehicles to school, they'll take 2 home, and that's why it becomes 4. Well, how can we find the expectation in this situation? We can do what we've done previously, where we just process it again. We multiply the top row with the bottom row. We multiply the outcome with the associated probability, and then we sum all of those together. Or, and here's where the coding comes in, or we realize this is the expectation of 2x, which is equivalent to 2 times the expectation of x. It's equivalent to double the expectation of x. So we can actually just double our 2.4 and quickly get an answer of 4.8 without having to reprocess the calculation that got us the expectation in the first place. Okay, so just to follow through the context, this would be how many vehicles a student uses in a school day if they also went on a school trip in the middle of the day. The x value has been coded and we get 2x plus 4. So either way, the x value has been coded and now we have 2x plus 4 in the top row. You can track back to the original table and you can see each of those outcomes has been multiplied by 2 and then we've added on 4. Once again, I could calculate the expectation the same way you know how to so far, or we can just process it like this. The expectation of 2x plus 4 equals 2 times the expectation of x plus 4. Putting this all into our calculation, we get 2 times 2.4, and when we actually process the calculation, we get 8.8. I've shown you this example with a random variable that only had 3 outcomes, so we're saving a little bit of time in comparison to working it out from scratch. What if this random variable had 10 different columns? If it had 10 different outcomes? Then you can really see the benefit of us using linear coding to find our new values. In some instances, you may not even have the original discrete random variable. You may not have this table or a function at all. You may just have been told the expectation of x and then needed to modify it from there. Let's have a look at a few more examples. So, the expectation of x plus 10. This means we added on 10 to all of the original values, and we want to know the expectation of that new distribution. That will be the same as finding the expectation of the original distribution and adding on 10 to that answer. Expectation of 3x. This would mean all the original values have been tripled. They've been multiplied by 3. We could find that by multiplying the original expectation of x by 3. And here's a bit of a combination of both. So if the original values were multiplied by 3 and had 10 added to them, we could find that by using 3 multiplied by the original expectation of x and then added on 10. It's slightly different for the variance. Now you may recall from straight maths that adding and subtracting does not change the spread of the data. And since the variance is a measure of spread, adding and subtracting will have no effect on the variance. Whenever we have a function like this, a function within the variance statement, we will ignore any and all adding and subtracting. So, in this case, each of the original values had 10 added onto them. We're going to ignore the add-on 10. The variance of that new distribution is the same as the variance of the original distribution. Here, each of the values were multiplied by 3. Multiplying and dividing, we are going to respect when we're looking at the variance. Each of the original values was multiplied by 3. The variance is going to be 3 squared times bigger. It's going to be 9 times the variance. The reason for this is because the standard deviation, now that's the value that is 3 times bigger. Since the variance is the standard deviation squared, the variance is 9 times bigger. Whenever we bring a value to the front of the variance statement, it must be squared. And finally, if we'd multiplied all the original values by 3 and added on 10, we ignore the add-on 10 and we make the question just like it was in the one above. We ignore the add-on 10 and we just process variance 3x. And for the same reasons I said before, we get 9 variance x. I can generalize that for you with these two formulae. If x is a random variable and a and b are constants, the expectation of ax plus b is going to equal a expectation of x plus b. When working with the expectation, we consider anything that's multiplying or dividing x and anything that's being added or subtracted to x. The variance of ax plus b is going to equal, firstly, the variance of ax, because we ignore the adding and subtracting, and then it's a squared variance of x. We square the coefficient of x inside the variance statement. So, linear coding for you in year 12 is making sure that you can apply these two results. If you notice, throughout the whole lesson, I've been talking about linear coding. This shortcut, if you like, only works if we've coded linearly. So, only if we've been multiplying and dividing, adding and subtracting. If we were squaring or square rooting, if we were working with indices or logs or trigonometry, none of these would work, since those are not linear processes, those are not linear operations. So, this is true for linear coding. So here's a few examples of linear coding in effect. How would we process these? I'll give you a few seconds to have a think for yourself, and then I'll reveal the answers. Here we're squaring the 4 on the outside. Here we're ignoring the add 1. We're going to ignore plus 2 and we're going to square the 3 on the outside. Sometimes there are equivalent forms of a correct solution. Here's 2 of them. On this one, just being careful, I've rewritten the inside of the bracket as 2 fractions. I can ignore the subtracting a half, and the coefficient of x, the half, needs to be squared as it comes outside of the bracket, leaving us with a quarter variance of x. So just a reminder, everything I've said so far is linear coding. If it's not linear, we cannot use this shortcut technique. Now, linear processes, linear operations include adding, subtracting, multiplying, and dividing. Non-linear processes, non-linear operations are such as squaring, square rooting, anything involving powers, logs, exponentials, and trig functions. None of these are linear, so our technique won't work. Looking at this example here, we could calculate the expectation of sine x. We're going to put the angles 30 and 60 into the sine function and multiply by the associated probabilities. So sine 30 multiplied by 0.2 and sine 60 multiplied by 0.8. That gives us an answer of 0.793. Let's see what happens when we calculate sine expectation of x. Our expectation we'll find just by multiplying 30 by 0.2 and 60 by 0.8. If we take the sine of that value, we get negative 0.558. The expectation of sine x does not equal sine expectation of x. So just be vigilant and make sure you're only trying to apply this technique to linear functions. These are not equal to each other. We cannot use this shortcut technique.